Here we have a 16 kilogram half cylinder that is placed on a hard flat surface as shown and released from rest at position 1. Let this be position 1. We're interested in determining the maximum angular velocity as it rocks back and forth. So let's say it is released from position 1. And observe that maximum velocity occurs when the semi-cylinder is in this position. I label this as position 2. Let G be the mass center of the cylinder. Then as it rolls, observe that it has plane motion, assuming that it is rolling without any slippage. Its mass center has a linear velocity as well as the whole object has a angular velocity. So let's say that it rolls in this direction and will have some angular speed omega, and when it reaches to this position 2, its linear velocity is perpendicular to radius of rotation. So as it rolls and reaches to position 2, velocity at this point, mass center G, is going to be, let's call it V sub G. And since the point of contact is right here, its radius of rotation at this instant at position 2 is this. V is perpendicular to radius of rotation. I label the radius of rotation with lowercase r, not to be confused with radius of the cylinder, which I label with cap r. So let's say this is cap r, which is equal to half of the diameter or 0.25 meters. Now if you look up the table of properties for this shape, mass center is located at this distance. Let's show this distance and call it delta H. This distance. The formula is given as 4r over 3 pi. Delta H equals to 4r over 3 pi. R being 1/4, if I multiply it by 4, then this distance I call delta H will be 1 over 3 pi if you want an exact value. Approximately it's going to be 0.1061. So let's say this is distance delta H. Then what I want to do at this point, also get some other properties for center of gravity G out of the table. If you look it up, Ig, mass moment of inertia about mass center Ig, you'll find this formula: 1/2 minus 16 over 9 pi squared times mr squared. Cap r being radius of the cylinder, again not to be confused with radius of rotation, which I've labeled as lowercase r. So as far as finding the angular velocity omega is concerned, I can use again work energy principle, which says work equals to change in total kinetic energy delta Ke plus change in potential energy delta Pe. Observe that since there is no external force applied to this object, work is 0, and because I have plane motion, I have both an angular speed omega and a linear speed v. Then I have two components for change in kinetic energy: 1/2 Ig omega squared plus 1/2 m Vg squared. And as far as potential change in potential energy is concerned, observe that mass center G is lowered to a secondary position as shown in the diagram. Therefore, there is a decrease in potential energy, which is minus mg, and change in vertical elevation from position 1 to position 2 is what I've labeled as delta H. So that's what I'm gonna have for change in potential energy. Assuming that motion occurs without any slippage at point of contact, then I can say velocity Vg equals to r omega, lowercase r times omega of the object, which is the angular velocity. So if I refer to the equation that I've written, the two unknowns omega and Vg can be reduced to one unknown if I apply for Vg in terms of r omega. So let's do so. Then I have 0 equal to 1/2 Ig, which is 1/2 minus 16 over 9 pi squared m cap r squared times omega squared plus 1/2 m Vg squared, which is going to be lowercase r squared omega squared minus mg delta H. Therefore, at this point, my equation has only one unknown omega squared. So if I do the numerical calculation, I can then solve for omega. Observe that all terms have m and the other side is 0. Therefore, I can cancel out m to simplify my calculation. I also multiply both sides of the equation by 2 to cancel the 1/2 and throw gh to the other side. Therefore, I'll have 1/2 minus 16 over 9 pi squared quantity cap r squared, I should say, omega squared plus lowercase r squared omega squared equal to 2g delta H. Then I can factor out omega squared and solve for it, which gives me 2g delta H divided by 1/2 minus 16 over 9 pi squared cap r squared plus lowercase r squared. So then at this point I can go ahead and plug in the values and eventually find omega. Then this gives me 2 times 9.81 times delta H. Delta H, as I have it here, is 1 over 3 pi, or you can use the numerical value, the decimal value, which is approximate. Then in the denominator I have 1/2 minus 16 over 9 pi squared times big R squared, which is 0.25 squared, plus lowercase r squared. Note that from the diagram I can write lowercase r to be equal to cap r minus delta H, which is 0.25 minus 1 over 3 pi. This turns out to be 0.1439. So going back to this fraction, I want to add 0.1439 squared. So this gives me omega squared equal to 51.15. Taking square root of it gives me omega equal to 7.1 radians per second, which is the desired maximum angular velocity, which occurs when the semi-cylinder is in horizontal position. Observe that as time goes on, omega turns this in clockwise direction, and the cylinder rolls up to come to a standstill, and then it rocks back and forth.